Welcome back to the session Solution of Simultaneous Equations. In the previous session, we discussed two methods, namely Gauss elimination method and Jordan method, to solve a simultaneous system. Here, we shall discuss another method known as method of decomposition or triangularization method. Here, we decompose the coefficient matrix of the system into two matrices. First one is a lower triangular matrix and the second one is an upper triangular matrix. For convenience, consider the system A11x1 plus A12x2 plus A13x3 is equal to B1. A21x1 plus A22x2 plus A23x3 is equal to B2, and A31x1 plus A32x2 plus A33x3 is equal to B3, which is a system in three unknowns containing three equations. This system can be expressed in the matrix form as Ax is equal to B, where A is the coefficient matrix, X is the column matrix of unknowns, and B is the column matrix of constants in the right hand side of the system. Let A equal to Lu. We decompose the coefficient matrix A into two matrices, where L is of the form, or L equal to the lower triangular matrix 1 0 0, L21 1 0, L31 L32 and 1. This is a lower triangular matrix, and U is equal to, U is of the form U11 U12 and U13, 0 U22 U23, and the third row is 0 0 U33. This is an upper triangular matrix. Hence, the given system can be expressed as Lux is equal to B. We use A equal to Lu. The system can be expressed as Lux is equal to B. If we set Ux as y, that is, if we put Ux equal to y, the system will become Ly is equal to B, which is equivalent to L is here the lower triangular matrix, y is a column matrix of three unknowns y1, y2, y3. Then Ly is equal to B gives 1 0 0, L21 1 0, L31 L32 1, y is column matrix of three unknowns y1, y2 and y3 is equal to B. B is the constants in the right hand side, which is equivalent to y1 plus 0 is equal to b1, that is y1 is equal to b1, L21 y1 plus y2 is equal to b2, and L31 y1 plus L32 y2 plus y3 is equal to b3, and can be solved for the unknowns y1, y2, y3 by the forward substitution. When y is known, the system becomes u11 x1 plus u12 x2 plus u13 x3 is equal to y1, u22 x2 plus u23 x3 is equal to y2, u23 x3 is equal to y2, and u33 x3 is equal to y3. This is the equivalent system and can be solved for the unknowns x1, x2, x3 by the backward substitution. We shall now describe a scheme for computing the matrices L and U and illustrate the procedure with a matrix of order 3. We have one zero zero matrix 1 0 0, L21 1 0, L31 L32 1 into, this is the L matrix, lower triangular matrix L, into the upper triangular matrix U11 U12 U13 0 U22 U23 and 0 0 U33 is equal to A11 A12 A13 A21 A22 A23 A31 A32 and A33. That is A equal to LU, which is of the form the coefficient matrix A is equal to product of the two matrices L and U. Multiplying the matrices on the left hand side and equating the corresponding elements both sides, we will get U11 as U11 is equal to A11, U12 is equal to A12 and U13 is equal to A13. L21 U11 L21 U11 is equal to this entry A21. This implies L21 is equal to A21 divided by U11. L31 U11 L31 U11 is equal to this first entry A31. This implies L31 is equal to A31 divided by U11. A31 divided by U11, that is A31 divided by U11 is A11. Here U11 is also A11. Now, L21 into U12 plus U22 is equal to this Henry A22. This implies U22 is equal to A22 minus A21 divided by A11 into U12. U12 is A12. And L21 U13, L21 U13 plus U23 is equal to this Henry A32. This is A23. Here is equal to A23, which implies U23 is equal to A23 minus A21 divided by A11 into A13. Again, L31 U12, L31 into U12 plus L32 into U22 is equal to A32, which implies L32 is equal to A32 minus A31 by A11 into A12 all divided by U22. Lastly, L31 into U13 plus L32 into U23, L32 into U23 plus U33 is equal to A33, from which U33 can be computed. Thus, we have a systematic procedure to evaluate the elements of the lower triangular matrix L and the upper triangular matrix U. First, we determine the first row of U and the first column of L. Then, we determine the second row of U and the second column of L. And finally, we computed the third row of U. The procedure can be obviously generalized. When the factorization is effected, the inverse of A can be computed from the formula A inverse is equal to A inverse is equal to LU inverse, that is equal to U inverse into L inverse. Now, we have an example. Solve the equations 2x plus 3y plus z equal to 9. X plus 2y plus 3z equal to 6 and 3x plus y plus 2z equal to 8. We have to solve this system using the decomposition method. Here we have the coefficient matrix A is equal to 2, 3, 1, 1, 2, 3, 3, 1, 2. This is the coefficient matrix. Let us assume this coefficient matrix is equal to that is A is equal to LU, where L is the lower triangular matrix, U is the upper triangular matrix. We can write like this, that is 1 0 0 L 2 1 1 0 L 3 1 L 3 2 and 1 into U 1 1 U 1 2 U 1 3 0 U 2 2 U 2 3 and 0 0 U 3 3 is equal to the coefficient matrix 2 3 1 1 2 3 3 1 2. Multiplying the left hand side and equating the corresponding terms, we will get U 1 1 as 2, U 1 2 is equal to 3 and U 1 3 equal to 1. L 2 1 into U 1 1 is equal to 1, so that L 2 1 is equal to 1 divided by U 1 1, that is 1 by 2. L 3 1 into U 1 1 is equal to 3, which gives L 3 1 is equal to 3 by U 1 1, that is 3 by 2. We have the equations L 2 1 U 1 2 plus U 2 2 is equal to 2, which gives U 2 2 is equal to 1 by 2, and L 2 1 U 1 3 plus U 2 3 is equal to 3 gives U 2 3 equal to 5 by 2. On simplification, we will get U 2 3 equal to 5 by 2. Again, L 3 1 U 1 2 plus L 3 2 U 2 2 is equal to 1. From which we will get L 3 2 is equal to minus 7. We have L 3 1 U 1 3 plus L 3 2 U 2 3 plus U 3 3 is equal to 2, which gives U 2 3 is equal to 18. It follows that the matrix A is equal to one 0 0 1 by 2 1 0. We substitute all these values of the lower triangular matrix and upper triangular matrix. We will get A is equal to the matrix 1 0 0 1 by 2 1 0, 3 by 2 minus 7 1 into 2 3 1, 0 1 by 2 5 by 2 and 0 0 18. And the given system of equations can be written as this into x y z is equal to 9 6 8, that is of the form Ax equal to B, where A is decomposed into a product of two matrices, that is 1 0 0, 1 by 2 1 0, 3 by 2 minus 7 1, this matrix into y 1 by 2 y 3 is equal to 9 6 8, the column matrix 9 6 8. On solving by the forward substitution, we will get y 1 as y 1 is equal to 9, 1 by 2 y 1 plus y 2 is equal to 6 gives y 2 equal to 3 by 2. 3 by 2 y 1 minus 7 y 2 plus y 3 is equal to 8, implies y 3 is equal to, putting y 1 and y 2 in this, we will get y 3 as y 3 is equal to 5. Hence, the solution of the original system is given by the matrix 2 3 1, 0 1 by 2 5 by 2, 0 0 18 into x y z is equal to 9 3 by 2 and 5, column matrix of 9 3 by 2 and 5. By back substitution, we can find the unknowns x, y and z, that is x is equal to, from this z is equal to 5 by 18, y is equal to 29 divided by 18 and x is equal to 35 divided by 18. That is, the solution of the given system is 35 by 18, x is 35 by 18, y is 29 by 18 and z is 5 by 18. This is the decomposition method or triangularization method. Thank you for listening this session. We will meet again with another topic in the next session. Thank you all.